Hello, everybody. A little bit of a change of scenery today. I decided to be rid of the mop. I am back today, December 3rd, 2024, and we are going to be diving into chapter 3 today of data structures and algorithms in Python. My name is Michael. I hope you're having a wonderful day. I'm a beginner programmer, learning and teaching myself after my 9 to 5 job. Um, just trying my best to hold myself accountable, provide resources for other people that might be in a similar situation, and just learn as much as I can with these resources that we've been given, um, you know, and there you have. So, yeah, I appreciate you guys joining me today. Let's go ahead and connect to the stream here, and then let the Discord know we are live. All right. Cool. So I'm super excited to start chapter 3 here. Page 111, we're making a lot of progress. By the end of chapter 3, we'll be almost at page 150. So, and then chapter 4 maybe into 200. So that'd be kind of really cool. We're chunking along here. I think it's motivating, oh, we've come this far. We're almost, it's good to know that you're making progress. Sometimes it can feel monotonous, but this is going to be fun. So I've actually, well, still, hello, thank you. Hopefully I pronounced your name correctly. I appreciate you joining my stream this evening and saying hello. Thank you so much. How are you doing today? All right, so today we are actually going to, for chapter 3 and chapter 2 and 1, we didn't really take any notes because we weren't really introduced to a lot of new topics personally. We were just kind of giving a lot of review, but stuff was quite thorough. So it was a lot of good refresher and good practice. But in chapter 3 here, we're going to be introduced to a lot of new concepts. So it's going to be important that we kind of jot down definitions as we go. I'm not going to be super thorough. Obviously, we have the book we can always go back into, but just to jot down the most important things that we find. And yeah, and then we'll obviously do the problems at the end of the chapter, like we have been doing so far on the stream. What brings you to the stream so far? You learning Python or anything? Teaching yourself programming? Are you a student or? I'm graduated. I graduated back at the beginning of 2020, or sorry, the end of 2021, very end, beginning of 2022, and I have a bachelor's of science in human biology and a minor in chemistry side of that, and yeah, I work as a formulation chemist at a biotech company, and I'm just trying to learn how to program after my 9 to 5 job, trying to keep myself, disciplined with teaching myself new skills, and I think programming is kind of in the similar area that I am in, and it could be a good. That's kind of what sparked this whole thing. So let me know if you have any questions regarding that. And I've been programming for teaching myself for about 6 months here. I created a few projects, and I've been just streaming my progress here. Every day, hopefully, try my best. I started pretty diligently for the past, 2 months or so, but I started programming about 6 months ago, but I didn't really start taking it super seriously until about September. So, yeah. Okay, let's dive in here while we chat with you guys. So we're on chapter 3 here, super algorithm analysis. So we're diving in. We're learning new concepts here. So this is going to be different. We might not be able to move as quickly, but we will have fun doing it. In a classic story, the famous mathematician Archimedes was asked to determine if a golden crown commissioned by the king was indeed pure gold and not part of silver as an informant had claimed. Okay. Archimedes discovered a way to perform this analysis while stepping into a bath. He noted that water spilled out of the bath in proportion to the amount of water that went in. Okay. Yeah, buoyancy. Realizing the implications of this fact, he immediately got out of the bath and ran. Sorry, I'm losing my breath here, guys. Need to. Whew. I was talking to guys. I'm excited to learn and be here with y'all. So sorry, I'm gonna lose my breath. Okay. And I cut off all my hair also too. By the way, in my past streams I had really long hair, and I usually grow it out, and I get a haircut about once a year. And today, yeah, today was that day, so off it went, and the restart begins. And yeah, all right. Well, still says I'm a senior right now studying computational math, and I'm trying to learn web development. That's really awesome. Computational math. I started taking the an MIT computational math course, like discrete math on a few weeks back, and I got through the first lecture, recorded it, uploaded it, and then I started the second lecture, and the first 15 minutes took me an hour and a half. And I was like, how am I gonna upload this? Like, it's gonna take me forever to edit down. And, oh, because like I was just trying to learn they were showing like the going through the example proofs that have already kind of been established and really quickly like proving like you can't divide by zero. I don't know, yeah, stuff like that. And um, anyways, a proof like irrational number or something. And I was just trying my best to go through it step by step because they just go through it so fast. Like if people are on, I just can't believe that no one in those classes asks any questions either. That they just breeze by all these things so quickly. I just cannot believe that all those people really are getting it like just right then and there. It's crazy. Um, yeah, I'm in biotech. I work as a formulation chemist. I make a lot of biological controls and testing devices for diagnostics in patients and stuff like that. Things you run, um, to diagnose patients for diseases, and you run my controls with them, and that's literally what I make in my labs. And so in various forms and for various components and diseases and things like that, and some other kits and products and stuff as well. But I mainly do a lot of biological stuff. So I'm just doing this as a way to continue learning and getting myself additional skills. And if it leads to anything, that's fantastic. And if it builds upon what I currently am doing, that's fantastic. I'm not keeping any. I think it's key to not put too much pressure, um, because once you start putting pressure, it no longer becomes fun, from what I found, right? And I want this to be fun and enjoyable, especially for everybody on the stream and for myself, because I want to keep doing this. And in order to enjoy and want to do the streams and keep doing it, I got to enjoy it. So, anyways, let's keep moving here. The discrete math was yeah, it was really bad. It was strugg. It was so I'll go back. I will go back. I might read a book maybe on it, but okay. He noted that water. Okay, realizing this, yeah, he ran out. Eureka, Eureka! After he discovered the analysis tool displacement, which, when combined with a simple scale, could determine if the king's new crown was good or not. That is, Archimedes could dip the crown and an equal weight amount of gold into a bowl of water to see if they both displaced the same amount. This discovery was unfortunate for the goldsmith, however, for when Archimedes did his analysis, the crown displaced more water than an equal weight lump of pure gold, indicating the crown was not, in fact, pure gold. Ooh, I'm sure that guy died. In this book, we are interested in the design of good data structures and algorithms. Put Simply put, a data structure. Here we go. Let's do like a definitions. Right, we have a data structure. A systematic way of organizing and processing data. Right? And we have a algorithm, which is a step by step procedure for performing some task in a finite amount of time. Okay, a step-by-step procedure for performing some task in a finite amount of time. Okay, so not infinite, but a finite, a certain. Okay, amount of time. These concepts are central to computing, but to be able to classify some data structures and algorithms as quote-unquote good, we must have precise ways of analyzing them. The primary analysis tool we will use in this book involves characterizing the runtimes of algorithms and data structure operations, with space usage also being of interest. Okay, here we go. The primary analysis tool we use in this book involves characterizing the running times of algorithms and data structure operations, with space usage also being of interest. So we need to keep in mind the time it takes to actually run these operations as well as the space it takes up. Running time is a natural measure of quote unquote goodness. Since time is a precious resource, computer solutions should run as fast as possible. In general, the running time of an algorithm or data structure operation increases with the input size, although it may also vary for different inputs of the same size. Okay, yeah, so generally as you increase input size, so does your time to process that input. But although it may also vary different inputs of the same size. Okay, so again, that's interesting. Also, the running time is affected by the hardware environment, the processor, clock rate, memory, disk, and software environment, the operating system programming language, in which the algorithm is implemented and executed. All other factors being equal, the running time of the same algorithm on the same input data will be smaller if the computer has, say, a faster processor, or if the implementation is done in a program compiled into native machine code instead of interpreted implementation. Okay, so what this basically says is that your runtime is also impacted by, physical hardware, such as the person's processor, memory speeds, clock rate, disk speeds, as well as software environment, their operating system, and programming language. So in programming languages like Python, I believe, they are interpreted, right? They have an interpreter, which then translates that into something else, right? Whereas other languages just directly convert into machine code, which can be considered faster. Interesting. So let's type in like running time here, and then let's type in what was it? We wanted running time and space usage. So as we get some more information about, I'll fill these in. Yo, Luis, yes, new haircuts. Thanks for noticing. I appreciate you, man. We are also almost to very close, I think 4 away from 200 subs. So super, thank you so much, you guys. Blasting off here on the channel the past couple of days. It's been really awesome to see things kind of working out here for the stream. Somewhat. Okay. So the runtime is a natural measure of quote unquote goodness. A natural measure of quote unquote goodness. Since time is a computer solutions should run as fast as possible, right? Okay. So space usage, like memory. So I'm sure we'll get some information about that. So, all right. Hey, 404, 540, sorry, not 404, 540. This is Data Structures and Algorithms in Python. It's a book that's taught, I think, at some college level courses of Python. I'm just reading through it myself personally and doing the practice problems inside and really grinding through and taking it all in and learning it independently here with the stream, obviously, and with you guys. You can just Google this, or you can join my Discord link below, where I kind of just conglomerate all of my resources I'm studying into one environment, so everybody can access them and have it kind of be easier that way, rather because sometimes it can be hard to decide where to jump in, and I kind of have not really like laid out a pathway because I don't really not really guiding people to follow me really. It's kind of more of a this is what I did, take it with a grain of salt, I guess. Hey, hello, Doc Kid. Thanks for joining back today. I appreciate you coming in. It's good to hear from you. I started reading the same book last night, skipped most of chapter 1 and started exercises because I know Python basics fairly well. I'm going to read chapter 2 and beyond. Yeah, chapter 2 really gives a good overview and deep dive back into classes and the dependent functions that custom classes make. Yes, almost at 200. Thanks, 540. I appreciate you. We're so close. Thank you for joining, man. All right. Okay, let's continue here. Focusing on running time as a primary measure of goodness requires that we be able to use a few mathematical tools. Okay. In spite of the possible variations that come from different environmental factors, we would like to focus on the relationship between the running time of an algorithm and the size of its input. Okay. So let's not focus on the environment factors because we can't really control those. If someone just has a slow computer, well, just get your computer up, just get it, but easier said than done for. So that's kind of something out of our hands, unfortunately. We have to have system requirements to run some programs in like games, for instance. But we can try our best to make those games run as smoothly as possible to get people of as many devices to access them. It kind of works hand in hand as a byproduct that way. So we are interested in characterizing algorithm's running time as a function of its input size. Okay. But what is the proper way of measuring it? In this chapter, we quote unquote roll up our sleeves and develop a mathematical way of analyzing algorithms. So this is where we get into like the time notation, I bet you. Appreciate you guys joining. Yeah, we got a haircut. I know people. It's kind of crazy. The lady. I just go to like this random place, and she was like, she started cutting my hair, and afterwards she's like, "Whoa, like you look so different." I was like, yeah, everybody says that usually. So I usually get a haircut about once a year. Just let it grow out. I don't really care. I kind of like it. It's natural, and I just let it be. It's fun, and I'll just get a haircut about once a year, let it grow out. It saves me a couple of bucks too, and then I'll just chop it about once a year. Yeah, I said that like 5 times. Sorry. All right, let's jump in here. Experimental studies. Um, so this was 3.0. So I'm just gonna do like 3.1 experimental studies. Right, here we go. If an algorithm has been implemented, we can study its running time by executing it on various test inputs and recording the time spent during each execution. Okay? A simple approach for doing this in Python is by using the time function, time function of the time module. Okay? This function reports the number of seconds or fractions thereof that have elapsed since a benchmark time known as the oh boy. Anyone want to give this a go? I'm not gonna front you. How do you pronounce this word? Is it epoch? Epic? Oh, I don't know. Sorry if this is so dumb, but it's typically pronounced epoch. Eel. Epoch? Epoch. While American English common. Well, okay, epoch. 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 All right. All right, here we go. So thank you guys for the help. So we got definitions here. So we have the epoch, which is the function reports the number of seconds or fractions thereof, such as an elapse that have elapsed since a benchmark time known as the epoch. Since a benchmark time known as the epoch. Is the epoch the benchmark or the amount of time that is reported? It didn't provide me the definition. Okay, so this function, the choice of the epoch is not significant to our goal, as we can determine the elapsed time by recording the time just before the algorithm and the time just after the algorithm and computing their difference as follows. Oh, so epoch is not the time that elapsed, it's the benchmark. Since a benchmark time. Okay. A benchmark time. For when to start recording an algorithms runtime, right? I think that was my interpretation of it. So, like, you'd have your epoch would just, like, you could have some function, right, that happens here, and then at this point, you start your time, run the algorithm, and then you just kind of chunk it out. The choice of an epoch is not significant in our goal. We can determine the time last from time import time. So you have time module is so returns the records and can return the elapsed time between 2 points in a program. Toast Dev, thanks so much. Appreciate the kind words about the haircut. You're awesome. Thank you. Welcome back. We are in chapter 3 here. So we have time module. Okay, and then so you just do time like this. Like so. To call. This takes a timestamp during the program's runtime. Pretty much. I think takes kind of like a timestamp. Okay. So we can import it, right, and then just it saved the time at that current point, run the algorithm, end time, and then we can just return that elapsed time to see how long it took to run that algorithm actually. Motivation stream, less than 1 week till finals. Oh, keep grinding, boys. Keep grinding. It's tough out there. I remember finals, it was tough. I was in the library all the time, stressing. I would put in some days just like for biology courses. The amount of material they want you to know for some of these exams is just ridiculous. Like, you're much more suited to learn it over the course. I know you're trying to get it done in a certain amount of time, but it's just crazy, especially like I don't even just the amount of concepts covered and forced down your throat is just nuts. It just doesn't make any sense. That's why I'm doing this independently rather than maybe going back to school, because it just one, the market's hard for anybody. A, two, I already kind of have a degree and have work, right? Three, I enjoy what I currently do as well. Four, um, you know, like I said before, why pay thousands of dollars to be stressed and then to just take maybe a little bit longer and learn it myself. And yeah, it might be a little bit hard. I won't have a physical piece of paper, but maybe I can show it and I can express my knowledge in other ways. So we'll see. And then back to A2Z slash leak grind. Returns the elapsed time since the epoch time. Oh. So between the epoch time, right? Give me a def in terms of algorithms. In the context of algorithm, epoch refers to one complete pass through an entire dataset during training or processing. This term is commonly used in machine learning and optimization in algorithms, especially for training neural networks. Okay, we don't want to get into during epoch. During each epoch, the algorithm processes all the input data, adjusts the model parameters based on the loss error, and prepare for the next iteration. For example, if you have a data set of 1,000 samples and train your model for 10 epochs, the model will see all 10,000 samples 10 times. See all 1,000 samples 10 times with the parameters. So each epoch is just the run of a um, so it's the benchmark time of a for an actual algorithm. So that's just what it is. It's the running of an algorithm, the complete processing. Basically a timestamp. Yes, the time returned. Hold on, let me get through this. So the benchmark time for when to start recording. Time. No, a benchmark time for reports the number of seconds or fraction thereof that have elapsed since a benchmark time known as the for an algorithm. Hate spelling this word over and over again. All right. Cool. So basically, a timestamp, yes, the time return will be irrelevant. That is whatever the value is, but you can subtract the end from the start and get the elapsed of your quote unquote work. Yeah. So you can just kind of save it as a timestamp, right? Basically a timestamp. Yes, the time return will be irrelevant in that one instance because it's just one frame because we want to know the difference of those two times. A benchmark, is this a benchmark? A benchmark time for an algorithm, maybe just for lack of better words. Okay, let's move on here. Okay, we will demonstrate use of this approach in Chapter 5 to gather experimental data on the efficiency of Python's list class. An elapsed time measured in this fashion is a decent reflection of the algorithm's efficiency, but it is by no means perfect. Okay, the time function measures relative to what is known as the quote unquote wall clock. Here we go. Wall clock. Because measured to relative to what is known as the wall clock. Okay, so meaning like a physical wall clock. Because many processes share use of a computer's central processing unit, the elapsed time will depend on what other processes are running on the computer when the test is performed. A fair metric is the number of CPU cycles that are used by an algorithm. Okay, so because you share processing power with other things on your computer, like I'm running VS Code here, but I also have the stream going. I also have, books open. I have this open. I'm using processing power in some capacity, relative small, but some capacity. So the time element still references all of that as well. Interesting. So let's make a note here for time module. Um, not a perfect uh, not a perfect way to measure algorithm runtime. Is runtime one word or two words? Oh well. Runtime due to, let's move this in. Not a perfect way to measure algorithm due to contrasting computing CPU power for other background applications on the because many processes share the computer's central process CPU, the elapsed time will depend on what other processes are running on the computer when the test is performed. Depends, so we'll copy this right here. So not a perfect way to measure code. Runtime depends on what other processes are running on the computer. When the tests are performed. Right. So it's not a perfect way to measure the algorithm runtime because it depends on what other processes are running on the elapsed time depends. Right, depends on what other processes are running on the computer when the test is performed. A fair metric is the number of CPU cycles that are used by the algorithm. Okay, this can be determined by using the clock function of the time module. Here we go. Right, so clock function of the time module, but even this measure might, a fair measure. So this measures the number of CPU cycles that are used by an algorithm, right? Measure the number of CPU cycles that are used by an algorithm. Real Nazar, thanks so much for coming back. I appreciate you joining again. Yes, thank you for the kind words about the haircut. I cut it off about once a year and just let it grow back after that. Save myself some moolah, and I like it just growing out too. My girlfriend doesn't mind too much, so yeah. Today was the day though. I was getting tired of it. I was getting tired of washing it, and it was getting in my face while I was studying, and it had to go. All right. You're basically learning intro operating systems in this book. Holy, yeah, it's pretty dense. That this book is, I've heard it's not for the faint of heart. So we're diving right on in. Good stuff. It has to do with concurrency. Anthony says, "Hey, Anthony, thanks so much for coming in." Ferris, thanks so much for coming in as well. I appreciate you. Welcome back, man. It doesn't depend on other processes, but it may be affected by other processes, meaning it won't be accurate. Okay, that's a better word of putting it. I was just kind of quoting them. Depend on what other processes. Oh, depends on what other processes. So we'll say depends on slash is impacted by depends on slash is affected by what other processes are running on the computer when the test is performed. Gotcha. Thank you so much for that added input, Ferris. That helps clarify things. Roland, thanks so much for coming in. I appreciate you stopping in, leaving a message. Hello to you. I hope you're doing well. This is Data Structures and Algorithms in Python. This is a book. It has three authors. I'm not sure exactly who their names are. I apologize, but you can just Google this book, DSA in Python, exactly like it is up here. Might be kind of small, I know. I'm sorry, but it's Data Structures and Algorithms in Python. Maybe I should, like I says in the title of the stream, uh, DSA in Python Chapter 3 I'm on right now. And or if you want just a simpler, just feel free to join the Discord below. And it's a completely free. It's just a conglomerate area of all of the study resources I've kind of compiled that I've used so far, such as the, sorry guys, I'm going to break out my typical spiel here. Fluent Python, haven't read this yet, but we're going to dive in soon. Gets into a lot of more intermediate and into some deeper level Python stuff, get more fluent and effective and efficient. I haven't started this one yet, but we have Python machine learning as well that we're going to dive in on the channel here and on stream. And then I'll have all the information about my studying in the Discord as well on this when we get to it. I think I don't have this one preloaded yet, but I do have the Fluent Python one preloaded in the Discord. But I have completed the Python crash course already when I was learning Python initially, and going back through on my channel and posting my solution videos to the try it yourself problems as a refresher to myself and as well as to help other people. So if that's something you're interested in, feel free to follow along to the channel. We are almost to 200 subs. We might even be crossed by now. Someone might have to let me know. So if we are, thank you so much, you guys. You guys are awesome. We are climbing up there really fast, and it's been a whirlwind, and I can't believe it. Honestly, I've been just shocked that people want to watch me do this, and it's really great. Well, I'm not shocked. I mean, my whole intention was for people to eventually maybe find this useful. So yeah, I'm happy that's working, I guess. All right, so the clock function in the time module, right, that Python provides measures the number of CPU cycles that are used by the algorithm, but we'll learn something about it here. But this measure might not be consistent if repeating the identical algorithm on the identical input and its granularity will depend upon the computer system. Interesting. So obviously, if you have a better CPU, maybe you will have more a faster speed, right? This depends on the clock speed of the CPU. I'm guessing just by the name of it. But even this measure might not be consistent if repeating the identical algorithm on the input. Okay, that's because its granularity will depend upon the computer system. It's kind of written kind of funny, but even its measure might not be consistent if repeating the identical algorithm on the identical input, comma, and its granularity. But why though? Because of this? So we'll say no depends on the CPU of the CPU hardware of the user, right? All right. Sorry, let me get caught up in some chats here. Could have finished this book, so W might. Thanks, Tosta. Well, hopefully, I'm only on chapter 3 here, so it might ramp up real quick and we might start getting slowed down, but we'll try our best to power through with your guys' motivation and help here. Minecraft Steve, thanks for joining. Yeah, I do have a previous degree. I graduated back at the end of 2021, and in bachelor's degree in human biology and a minor in chemistry of that kind of area. I really enjoyed the chemistry aspect, so I found work in biological chemistry as a formulation chemist. I work at a biotech company where I make a lot of biological controls used in diagnosing patients, like in hospitals and things like that. So, you know, I like in testing and specifically in testing and advanced biological levels and accuracy for accurate testing results for giving people diagnosis. That's the gist of it. Kind of on a more surface level, I guess. But yeah, so I'm just doing this after my 9 to 5, and then on the weekends I come on here about 7 to 9. Usually after my 9 to 5, if I and then some days I'm really tired and I might call it for that day. But I usually would try my best to come on here and stream every day and learn. I want to be consistent as I can. I really enjoy it, and I like talking to you guys. And yeah, but then on the weekends I like to stream for maybe 4 or 5 hours, and really get a good learning. I feel really productive when I do that. So yeah, because I don't really do much on the weekends besides hang around. So Eric, thanks so much for coming in. Roland says, I like watching this kind of content because I'm doing the same. Well, that's exactly my thought process. Maybe other people are in a similar boat, and it's can be kind of it can honestly be a little depressing to do it by yourself. I was doing it alone for myself, and you can feel easy to just give up and say, oh, it's so easy to just, want to just step away because you're just alone, and you can because you are alone. Um, but by doing this, it helps to create a more accountability. What motivated me, yeah, so the initial motivation was at work. I have to manually and intuitively calculate some pretty advanced theorem matrices using quite a lot of data points. So for instance, like I'm blending solutions together, many different solutions up to, like, in many different forms, and they all test at different ranges and different points for many different things, like um, they test like in your body, like all biological testing points, like think of on the simpler term calcium, sodium, like, but think of more like cancer antibodies and things like that on in yeah, so for more diagnostic things. But obviously, those more simplistic elements are in there, for lack of a better word. But um, so I blend them together, and I have to manually, like by hand and with like through my processes, calculate these expected outputs in theory, what they would be, and then go ahead and make a small version and then scale that up to the large product. And it's quite a large process. It's a huge multi-million-dollar biotech industry, and yeah, so we get it's pretty intense at times, and I'm on year 3. I'm going on year 3. I'm almost done with year 3 actually, and been through a promotion, and it's been fun, and it's it's neat, yeah. But I thought, I'm sorry, I'm getting sidetracked. I thought, why why am I doing this by hand? Like, I feel like a computer could do this. This is getting annoying. I mean, it's fun. But it's just like I could save a lot of time. So that started this rabbit hole. I never actually solved that problem yet. I still do it by hand. I actually had to do that same chemical matrix because I'm making this product, the same exact thing, this solution again. I had to do that matrix literally yesterday. Um, and so I spent about 3 hours doing that by hand. And so if I just had like a button that formulated it for me with an algorithm, then yeah, so now we're finally jumping into algorithms to maybe do that. And so we could actually get a project going after the small business manager that we're working on. So sorry about that spiel. I know that was a lot, but uh, that's kind of just my background. And yeah. Eric says, been doing dev work at a local startup for 3 years, and basically all I do is learn. It's crazy how many facets of software engineering there are to dive into rabbit holes like this with. Exactly. That's what I thought with, like, I think I can, really make a mark on my learning by taking a stab at this myself. He also says, my typical drug of choice now is NFC and UFC FRED desktop code from C++, JNI libs, and Kotlin desktop applications. It's nice to see people out there doing stuff like this. Well, honestly, I'm sorry, Eric, but a lot of that flew over my head. I'm not gonna front you, but hopefully one day we can speak the same language. I I'm still getting my feet wet here. I feel like I've learned a lot so far, but I have a long way to go. That's for sure. But we're still going one foot after the other, right? It's not every day. It happens not all in one day. It happens. People go to school for 4 years, and then they have to continue learning in an actual job. So I gotta, expect the same kind of level of effort. All right, sorry, we're getting sidetracked here. We gotta stay focused on the book. We're getting. Oh, sorry, my phone's ringing. Hey, I'm in my stream. Let me call you back. Okay. Sorry about that. Let me put myself on Do Not Disturb while I'm on the topic. Okay, let's get. So Anthony, that's a very good question. Anthony says, interesting. Why not just ask AI to make the program to solve the problem instead of going through tons of books to learn Python? I'm assuming at this point you're actually enjoying programming. That's exactly the reason. I could just ask AI to do it, but at the end of the day, like at my work, do I go tell my boss, "Oh, I have this program that AI wrote. Um, you know, here's this, right?" Or do I have go tell my boss, "Here's this program that I wrote." And I thought about it for a little bit, and I'd much rather have the utility at my disposal and at my power rather than it depending on something else. Now, I can obviously use the something else to aid in my development for sure. I do that every day in the stream. Right there, I command or uh, option space brings up my little quick access bar where I ask it questions from the text here. And you saw it yesterday. We solved the remaining chapter two problems with a lot of the help because they were kind of challenging, and we kind of got some aid and some assistance and nudge us to solve the answers and get the answers ourselves, and it was fun. But yeah, I much rather value learning the skill myself. I think there's definitely people might say it's a waste of time, but also you're progressing as a learner in general. Like I think you're getting smarter as a person by just learning in general, not even just computer science, but continue learning in any field. So I think it's a benefit just to continue to education in general. For sure, I understand I'm 5 years into my software as a career journey, and I have an imposter syndrome. Yeah, it can be challenging, but oftentimes I think about it as if I'm 3 years, into my profession now currently, and um, I produced good products for for my track record for my company, and um, you just have to remain confident, and even if things do go bad, they can come as a shock, right? And because they should come as a shock because you should remain confident in yourself that you are doing a good job and that you're. I think maybe that's just like turning a blind eye to the potential issues, but maybe just faking it till you make it is the kind of summary, I guess. I don't know if that's any. It's just me rambling. For real, it's never ending. I look forward to it. Of how low level do you want to get? Oh, motivated to learn systems. Yeah, gotcha. All right, let's keep going here. Um, a fair metric is the number of CPU cycles that are used by an algorithm. This can be determined by using the clock function of the time module. But even this measure might not be consistent if repeating the identical algorithm on the identical input, and its granularity will depend on the computer system. Python includes a more advanced module named TimeIt to help automate such evaluations with repetition to account for such variance among trials. Okay, we have time. Where was it at? It. Module. A TimeIt module. So because we are interested in the general dependencies of runtime on the size and structure of the input, we should perform independent experiments on many different test inputs of various sizes. We can then visualize the results by plotting the performance of each run of the algorithm at it as a point with x coordinate equal to the input size n and y coordinate equal to the runtime. Okay, so runtime yeah, got you. This figure 1.3 3.1 displays this. hypothetical data. So yeah, we have like an input size. As the input size increases over time, our running time naturally increases in a linear fashion. Now we might get to some point where the computer runs into a block and it can't handle data amongst a certain point, and you exponentially start to increase to where the computer no longer can input sizes at a efficient runtime past a certain point. So you might get like an asymptotic relationship on this x-axis here, parallel to the y, if I remember correctly from my days back in math. Yeah, Toast, a lot of people come in here and are talking about the AOC for 2024. I haven't taken a stab at it. I want to, maybe, I heard it's kind of challenging. So thanks so much for stopping in, people that are here. Thank you guys for joining me today. Okay. Display. The visualization may provide some intuition regarding the relationship between problem size and execution for an algorithm. This may lead to a statistical analysis that seeks to fit the best function of the input size to the experimental data. To be meaningful, this analysis requires that we choose good sample inputs and test enough of them to be able to make sound statistical claims about the algorithm's runtime. To be meaningful, this analysis requires that we choose good sample inputs and test enough of them to be able to make sound statistical claims about the algorithm's runtime. Okay, so you need to test sample inputs of varying sizes quite heavily in order to determine the efficiency of an algorithm. And then you can probably plot this over like you can probably get um, a slope of this average line formed, and then that can be your you can have like an equation that'll, yeah, exactly. So challenges of experimental analysis. While experimental studies of running times are valuable, especially when fine-tuning the production quality code, there are three major limitations to their use for algorithm analysis. Challenges of experimental, okay. Experimental running times of two algorithms are difficult to directly compare unless experiments are performed in the same hardware and same software environments. Experiments can be done only on a limited set of test inputs, hence they leave out the running times of inputs not included in the experiment, and these inputs may be important. Experiments can be done only on a limited set of test inputs, hence they leave out running times of inputs not included. Okay. An algorithm must be fully implemented in order to execute it to study its running time experimentally. Yeah, because if you're experimenting on actual subjects, well, your algorithm has to actually work um, and be fully implemented into some sort of like user interaction, right? So this last requirement is the most serious drawback of the use of experimental studies. At early stages of design, when considering a choice of data structures or algorithms, it would be foolish to spend a significant amount of time implementing an approach that could easily be deemed inferior by higher level analysis. At early stages of design, when considering a choice of data structure or algorithms, it would be foolish to spend a significant amount of time approach by higher level. Okay. Interesting. Yes, Jeremy, we are on our way there. There's a section about Big O coming up. We're about to get there. So if this is what you've been waiting for chapter 3, drum roll, we're almost there. Okay, so moving beyond experimental. So our goal is to develop an approach to analyzing the efficiency of algorithms that allows us to evaluate the relative efficiency of any two algorithms in a way that is independent of the hardware and software. So we want to, what we're talking about right now is we are wanting to test our algorithms, right? In order to do that, we need data or some sort of interaction, usually because algorithms need interaction or something to work with, from my understanding. And so like the closest thing I could think of is like social media algorithm. You need users to use the algorithm to over time to blend and whatever to make it work, whatever it's supposed to do. So um, we're trying to find an approach to do that here. Um, that's independent of hardware and software. is performed by, our goal is to approach, okay, and 2 is performed by studying a high level description of the algorithm without need for implementation. And 3 takes into account all possible inputs. Okay, counting primitive operations. To analyze, let me put these definitions actually up here. Oh no, these are definitions in 3.1. I'm just going to put these up here. All right. To analyze the running time of an algorithm without performing experiments, we perform an analysis directly on a high-level description of the algorithm, either in the form of actual code fragment or language-independent pseudocode. We define a set of primitive operations such as the following: assigning an identifier to an object, determining the object associated with an identifier. Okay, so assigning an identifier to an object, like a variable to an object, determining an object associated with the identifier, performing an arithmetic operation, for example, adding two numbers, comparing two numbers, accessing single element of a Python's list by index, calling a function, returning from a function. Okay. Oh, these are all primitive operations. Formally, a primitive operation corresponds. So what in the world are primitive operations? Formally, a primitive operation corresponds to a low-level instruction with an execution time that is constant. Ideally, this might be the type of basic operation that is executed by the hardware, although many of our primitive operations may be translated to a small number of instructions. Instead of trying to determine the specific execution time of each primitive operation, we will simply count how many primitive operations are executed and use this number t, how many primitive operations there are executed, as a measure of the running time of an algorithm. Any of you guys get that? We're really getting it here, guys. Okay, so a primitive operation corresponds to a low-level instruction with an execution time that is constant. Ideally, this might be the type of basic operation that is executed by hardware, although many of our primitive operations may be translated to a small number of instructions. Instead of trying to determine the specific execution time of each primitive operation, we'll simply count how many there are and use this number as a measure of the running time. Okay, so this operation count will correlate to an actual running time in a specific computer. Okay, so you're just counting all of these quote-unquote primitive operations that this algorithm performs, and those are the determining factor for how fast, or the running time of an algorithm. Now, how exactly do we, I'm sure we'll get there, but this operation count will correlate to an actual running time in a specific computer. For each primitive operation corresponds to a constant number of instructions. And there are only a fixed number of primitive operations, right? So if each primitive operation has a constant number of instructions and operates, essentially at the same speed every time, you could basically sum them. Is that what it's saying? State of the running time. So let's go with the chat here. Sorry, we're getting behind on chat. My bad, guys. It's kind of fun. We got a lot of chat. You guys are really awesome. This is so cool. Like, I literally can't stop smiling. It's cheesy as all can be, but It's true. Like I didn't expect all this. Jeremy says we're at Big O right now. Been at it for years. Still breaks my brain. All right. Well, hopefully we can do it together here, Jeremy. We're all in. Eric. Okay, we got some independent conversation. I do love fiddling. Okay, hold on. Sorry. Okay, Anthony says, I believe that he's saying is given that primitive operations are constant. If we ignore any other types of operations, you can count the number of primitive operations and set that to t. State the running time. This is without the utilizing big O. In other words, primitive operations are not dependent on input, so you can just count them. Okay, interesting. So let's go to GPT. Give me a simple explanation of primitive operations. Primitive operations are the most basic action a computer can perform during a program's execution. These include things like arithmetic operations, adding, the math, comparison, less than is or equals to, data access, control flow functions. Okay. So, the most basic actions a computer can perform during a program things like math, so like some examples of this are math, comparisons, data access, like is it like indexing? No, like accessing data points at indexes, right? Control flow, jumping to a specific target program, looping, just like looping. If so, looping, and then function calls. Okay, cool. These operations are primitive because they are basically performed directly by the computer's hardware without requiring complex computation. Okay, interesting. That helps. That helps clarify that a lot more. Um, mm, mm, mm. Measuring operations of a function as a function of input size. Okay. To capture the order of growth of an algorithm's running time, we will associate each algorithm with a function f of n that characterizes the number of primitive operations that are performed as a function of the input size n. Okay, so n is our input size. F of n is a function that characterizes the number of operations that are performed dependent on input size. Okay, so a function dependent on n. Section 3.2 will introduce the 7 most common functions that arise, and 3.3 will introduce the mathematical framework for comparing functions to each other. Focusing on the worst case input. An algorithm may run faster on some inputs than it does on others of the same size. Thus, we may wish to express the running time of an algorithm as the function of the input size. Sorry. So we may run faster on the same input than it does of the same size. Thus, we may wish to express the running time in an algorithm as a function of the input size obtained by taking the average of overall possible inputs of the same size. Okay, so we want to average out all the possible inputs at that same size. Unfortunately, such an average case analysis is typically quite challenging. It requires us to define a probability distribution on the set of inputs, which is often a difficult task. Figure 3.2 schematically shows how, depending on the input distribution, figure 3.2 shows how, okay. Depending on the input distribution, the running time of an algorithm can be anywhere between the worst case time and the best case time. For example, what if the inputs are really only types A or D? An average case analysis usually requires that we calculate expecting running times based on the given input distribution, which usually involves sophisticated probability theory. Therefore, for the remainder of this book, unless we specify otherwise, we will characterize running times in the terms of the worst case as a function of the input size n of the algorithm. Okay. Worst case analysis is much easier than average case analysis as it requires only the ability to identify the worst case input, which is often simple. Also, this approach typically leads to better algorithms. Making the standard of success for an algorithm to perform well in the worst case necessarily requires that it will do well on every input. That is, designing for the worst case leads to stronger algorithmic muscles, quote unquote, much like a track star who always practices by running up an incline. Okay, so that was a lot of information, but what I understand from this, if you are following with me, hopefully, uh, so by establishing, you can have the algorithms like we showed in this curve up here. These two samples are of the same size, right here. They align on this x-axis perfectly on the same point, from my eye. Now, these samples have the same size, but they have differing running times, meaning that these algorithms just ran slightly different for some sort of factors. Now, we can assume, right, we can say, okay, well, if we have a bunch of data, well, we can average those out. Well, now what it's saying is you have to kind of mathematically prove the averages, based on some sort of normal distribution at that point. And you'd have to do that, I'm assuming, for every single data size. And this can become quite statistically large from my statistics for statistics for science class back in college. I think it was 3,000, 3,100. It was my junior level course. I took it during COVID. I had to teach myself that class. That sucked. P-values, normal curves. Teaching myself that one was rough. That's right when COVID hit. So that would have been my junior blend into my senior year of college. So yeah, so instead of doing that, instead of trying to average out every possible scenario at that sample size for every runtime and plotting those normal curves and having those probability values associated with that average, like if we have that average, well, what's the possibility we do get that average, right? We don't want to, it's too much work. We just want to plan then for the worst case scenario. So we would, at this sample size, plan, for this obscene, so, we have 2 sets of data here. Maybe this one would be better. We have 3 sets. We would plan for this worst case scenario and improve based upon that. Now, that essentially, like what you're saying is, if you're putting yourself at a disadvantage from the start, in theory, what it's saying is that you will get better or perform better or have stronger algorithms, over time, as you improve the algorithm. Now, is that always the case? In theory, maybe, but what if you're so handicapped from the start that it's pointless? It can. That's also a point of view to take. So that's also interesting to think about. let's go back down here. Yeah, so let's look at this graph here. Yeah, so by planning for the worst case of that n size algorithm, right? So here we go. We have input instances. We have all of these different sizes, right? If you're n values, so A, I'm assuming is, and this took 5 milliseconds to run. B, oh, input instances. So I'm assuming maybe these are all of the same size, or they probably are to compare to at the same point. So this one took 5 milliseconds. This one took 3, 4, 5. So these are the worst case scenarios. So A and D is what we would kind of be our baseline. Gotcha. And our best, so and our average would be kind of a blend. So we'd have to mathematically show this distribution for our average, and I don't think they want us to really focus on that. Okay, let's catch up some chats here. For computer system, the face. Here we go. Love seeing someone learn this for the first time. Yeah, I'm sure I'm gonna get this like, what? I'm sure I'm gonna get that quite a bit. It can get so complicated. Mine was much worse. I still don't fully understand it. Tough. He is doing good. Thank you so much, Toast. I appreciate your kind words. You're very nice. You got this. This is why we focus on worst case. Yo, Vanch, hello. Thank you for the kind words. Yes, haircut. We chopped it all off. We doing something different here. So haven't had short hair for a while. So this channel's booming. Is it really? Let's check the let me drag this over. Let me check the channel here. I haven't checked it in a second. Super excited. 199. We're one sub away from 200, guys. That is so cool. Woo! We'll probably hit it before we end this stream. That's so cool. All right. So we have this. So I'm going to talk about so I'm going to say like let's do like counting primitive operations, right? So this will be like we can use maybe to big operation, although said we're trying to determine specific runtime. We can count the number of primitive and t and measure the runtime of an algorithm, right? So functions run so function of n, right, where we have characterizes the number of primitive operations that are performed as a function of the input size n, right? So then we have worst case scenario. The slowest observed runtimes of the algorithm used as the base level for improvement and worst case. Yeah, slowest observed runtimes of the algorithm used as the base level for improvement and yeah, okay. So we will refer to this, the worst case, right, as here we go. So Vance, yeah, thank you for the kind words, Vance. Appreciate it, man. You explained theory very experimentally perfectly. Thank you. That's very nice. Anthony says the idea is to always consider worst case scenario when optimizing algorithms, since this consideration leads to greater focus on minimizing the total number of operations needed. The slowest observed runtimes are not used as the base level for improvement. Focus. I'm gonna copy exactly what you said. That was perfect, Anthony. Um, Always consider the runtime. Okay, here we go. Like right here. There you go. Literally copy that in there. Thank you, dude. Always consider a worst case scenario when optimizing algorithms, since this consideration leads to a greater focus on minimizing the total of operations needed. Okay, here we go. 3.2. We're moving on here. So we have a time it module thing that we need to kind of. Where did the time it come in? Talked about time it. What was that again? Um, you should add tags in the description of the streams. You can get even more people. What kind of tag should I add in, Vansh? Is that like a good, like, you mean hashtags? Like Python? Yeah, I should add some of those. That'd be smart. So we'll go here, like this, make that go like this, tab in, like that. There we go. Okay. F of n is the time complexity. Also known as AKA quote time complexity. Okay, cool, interesting. Thank you so much for that. Okay, take a drink here. I'll come back to this time it module. I'll look that up later. Okay, it was somewhere in there. Forgot it. Okay, here we go. The 7 functions used in this book. Here we go. This is big. 7 functions used in this book. F of n is actually the function that performs the algorithm itself. Time complexity is written using big O notation. Okay. Yeah, I've heard of time complexity referred as big O notation. So f is the function and n is the size of the input. Causing, does it then cause, is it a correlation? Like, does it cause time complexity? Based on n? So what would, interesting. I don't think it's AKA, like also known as. because it's not the function. This isn't characterized as time complexity, right? So I think that's probably inaccurate to say that there. Ooh. The algorithm itself will determine the time complexity. Okay. This is just at that one instance and sample size for the algorithm f, function f. Or is f the primitive operation? Or is f the entire, So if given an input size of n, it is still possible to have an algorithm with a time complexity of n squared, for example. So if given an input size of n, it is still possible to have an algorithm with a time complexity of n squared. F of n is the number of primitive operations on the algorithm. Okay. Oh yeah, we're counting primitive operations. We can count it using okay, cool. Interesting. Okay, thank you guys for that. Let's move on here to 3.2. In this section, we briefly discuss the 7 most important functions used in the analysis of algorithms. We will use only these 7 simple functions for almost all the analysis we do in this book. Okay, this is going to be important. We gotta hone this in. Lock in here, boys. Lock in. In fact, a section that uses a function other than one of these 7 will be marked with a star. Okay, to indicate that it's optional. In addition to these 7 fundamental functions, Appendix B contains a list of other useful mathematical facts that apply to the analysis of data structures and algorithms. Okay, so here we go, boys. Number 1, constant function. So the simplest function we can think of is the constant function. This is the function. F of n is equal to c. Okay. We'll tab this in. Okay, this is the simplest function we can think of as the constant function. This is f of n of c. For some fixed constant c, such as c equals 5, 27, c equals 2 to the power of 10. That is, for any argument n, the constant function f of n assigns the value c. In other words, it does not matter what the value of n is. F of n will always be equal to the constant value c, because because f of n is directly is equal to c, right? So the overall count of primitive operations in a sense is equal to c. F of n will always be equal to the constant value c. Because we are the most interested in the integer functions, the most fundamental constant function is g of n is equal to 1. Because we are most interested in integer functions, the most fundamental constant function is g of n is equal to 1. And this is the typical constant function we use in this book. Okay. Note that any other constant functions, f of n equals c, can be written as a constant function c times g of n. That is, f of n is equal to c times g of n in this case. Oh boy. What did they just say here? So, because they're most interested in integer functions, the most fundamental constant function is g of n equals to 1. And this typical constant function we use in this book. Note that any other constant function, f of n is equal to c, can be written as a constant function as a constant c times g of n. Well, g of n is just equal to 1. So this is just the simplest form of a constant function as being just 1. Yeah, okay. So c would in this case just be multiplied by itself, whatever c is equal to, which is f of n. So in this case, the answer is just c still. Okay. As simple as it gets, the constant function is useful in algorithm analysis because it characterizes the number of steps needed to do a basic operation on a computer, like adding two numbers, assigning a value to some variable, or comparing two numbers. Okay, that was a lot. All right. Vance, he says I sent you some tags. Maybe you can use if you want. You can add more if you want, but those got from ChatGPT. I sent it to him private message. Okay, thank you so much. F of big N is going to be the function itself. What we set it equal to is going to be the actual time complexity. Okay. Oh, F of big N is the function. So got you. Congratulations on 200. Oh, we hit 200, boys. Let's hit a round of applause real quick. Celebrate. Celebrate. All right. That's so awesome. That's crazy. I was just literally like a month ago in here talking to myself, doing this day after day, and then uploading some videos and whatnot. And all of a sudden, a couple people started popping in, a couple more people started popping in, more and more. And next thing you know, we got a little group going here. So this is so cool, guys. Uh, on the road to 1K now. Yes, we're on the road to 1K. We'll have to do some big special. We'll have to brainstorm some specials. Ocelots, thanks so much for the love this content. Well, appreciate your comment. Thanks so much for stopping in. I appreciate you so much. That's really nice. Anthony says time complexity itself is going to be what describes the asymptotic behavior of f of n as n approaches infinity. Okay, yeah. So as and big N represents what again? So as big N approaches infinity, like the so f of n. So why are you guys using big N and not little n, whereas the book is using little n here? I'm confused on that notation. So f of big N equals c is simply the number of required operations, right, required by the algorithm, and not on the size, since it remains the same. Oh. Okay, so because we are not dependent on n in this situation of f of n is equal to c, this is just the number of, okay, got you, of operational functions, primitive operations, right? And big N is the input size. So then what is little n? Is little n also the input size? Are you guys just using them inversely? Not inversely. Coversely? I don't know. Regardless of how large or small the input is. This is N or N. Okay, both. Okay, got you. Sorry. In the United States, sometimes they teach like a large N to mean something else in some cases. And I've at least seen that in some of my math classes. I don't know if I'm just pulling that out of my butt though. But okay, so that clears that up. So big N. Okay, got you. Thank you so much. So in this case, then, if the constant is 5, no matter what, it will take 5. Now, 5 what, though? Like, what does this mean, like, in integer form? Like, why is this, like, in terms of 5? Like, why? So if f of n is equal to the number of operations needed in our function that are independent of sample size, no, it'd be dependent on sample size because f is dependent on n. 5 primitive operations. Okay, got you. So we'd have 5 primitive operations taking place in this algorithm that constantly happen no matter what, right? Like that's just how many for loops we have in our in our thing? How many while we have 27 while loops that were, some sort of constant operation, 27 functions we wrote in our program that, no matter what, that don't take in some sort of sample dependent thing that they have to run, right? So that's interesting. Okay. Um, so I'll go like this, paste that there, and I'll come back here and give a little blurb definition. If someone is interested, and I'll copy this right into the notes here, and we can have this be interactive, right? If someone is like we did before, if someone has like a definition for a constant function, like a quick blurb they think would be good to add here, feel free, and I'll paste it right on in. If we all agree on it, then let's add it in. Let's make this open source. Open source notes. That's funny. Okay, let's go number 2. Logarithms function. Okay, so toast dev says no, it's not 5 while loops. Okay, interesting. If the for loop depends on n, then that wouldn't be considered a constant operation. Okay, got you. However, in the for loop, if the for loop is always going to run for the example 5 times, then that would be considered constant. Okay, so there's levels to the constant. So you can be constant on like a local level, and then you can also, if well, that means if every function in your program depends on n, well, is every function then constant? Because they all, or would your c be 0? How about that hypothetical? If every function depends on the sample size, would your c be 0, or would your c be every function? However, if the for loop is always going to be run for the example if I don't, okay, might be nice to look at the graphs quick and you'll get an idea of the functions. Do they have graphs? Oh. You mean like just a logarithmic graph? Just like a, whatever, like a, what is it, just like a, like it goes like this, I think, right? Um, okay, so let's do this then. Let's go, it's a bar. Let's type in Desmos. So we have this here. So we have, but C's got to equal something, right? Yeah, so, okay, yeah, so it's just linear, right? Like it's just a parallel, we have a linear function here. Well, is linear, I can't, I feel so dumb. Is linear just a straight line, right? I think that means linear, or does it have to be at an angle, not 0? Okay, so then, okay. Ooh, why does it do that? I hate how it does that sometimes. Let me put this, come on, let me try to finesse this right here. Come on down. No. Come on down. Whatever. Oh well. Okay, so we have the graph pulled up. Five constant operations, for and while loop aren't constant. Okay. Yeah, look at the graph first, then come back. Graph, got you. For example, for I equals 0, I is less than 5, I plus plus is constant. I plus plus. For I equals 0, I is less than n, I plus plus, oh, add 1 to n, is not constant. Oh, because it remains less than 5. Okay, got you. The function always outputs 5. Got you. Regardless of the input size. 5 ops is likely the one comparison in return. I sent you a link, or you can just look up big O time complexity graph. Yeah, Desmos, right? This algebra 2, I remember just plugging everything into Desmos in my sophomore year of high school. For I equals 0, I is less than n, I plus plus is not. Oh, I'll let you guys debate all those. Okay, let's just keep moving here. So we have, now that we got that, now that we reviewed that, let's go back through and just give this one more go then. The simplest function we can think of is the constant function. This is the function, f of n is equal to c, for some constant fixed value c, such as c equals 527 or 2 to the power of 10. That is, right, if c equals 5, whatever. That is, for any argument n, the constant function f of n assigns the value of c. In other words, okay, so no matter the output, no matter the input, right, value, you just have an output of 5. Okay, that makes sense. So, functions that are independent of input size. No matter the size of the input, the function will return or result some value c. So like example, f of n is equal to c, right? Is equal to 5 for c is equal to 5, right? F of n is equal to 5. Output will always be 5. Okay? Interesting. Okay, so let's get to Cobb sheet. Yeah, I don't know C-like languages. I'm sorry. I only know Python. It's my only current knowledge. Sorry. The idea is that for any operation, if it has a dependency on the sample size, it's not constant because the number of operation grows proportionally to n. Exactly. Perfect. That was a great way of saying it, Anthony. Constant for I in range 5, not constant for I in range of n. Got you. Because range of n is dependent on the sample size. If you range 5, because you're getting the 5 range every single time. Okay, that makes a lot of sense. Perfect. Okay, so a constant, the constant function always returns the same value. Okay, so yeah, it's a function, right? So that, it produces the same value over and over again and is independent of the sample size because the value would grow as sample size grew, or some sort of, it had like an inverse relation to sample size that was programmed in and so on. But perfect, okay. That makes sense. Logarithm function. One of the interesting and sometimes even surprising aspects of analyzing of the analysis of data structures and algorithms is the ubiquitous presence of the logarithm function. F of n is equal to log b of n, log b for n times n, for some constant b is greater than 1. This function is defined as follows: x equals log b times n if and only if b of x is equal to n. b to the power of x is equal to n. By definition, log b of 1 is equal to 0. the value of b, so b to the power of 0 is equal to 1 because it's powering it to anything, it's itself. The value of b is known as the base of the logarithm. The most common base of the logarithm function in computer science is 2. As computers store integers in binary and because a common operation in many algorithms is to repeatedly divide an input in half. In fact, this base is so common that we will typically omit it from the notation when it is 2. That is, for us, log n is equal to log 2 of n. Oh, so if it's log just given by itself, you can infer that it has a base of 2. Now, I'm going to be front with you guys. It's been a long time since I did my calculus class and did pre-calculus into my logs. So if I am just not getting this or I'm slow, please bear with me, stay with me. It's all in process. We'll get it and then we'll master it and we'll solidify it. But I took my calculus class freshman year of college and then I never took a math class besides stats after that, and so it's been a while. So logs have a base value, okay, and is that just the starting point of the log? I'm not exactly sure what the base be. The most common base for log is 2, okay. So how does the base impact the log? In a sense, is it like a scalable factor? Is it a starting place? That's what I'm trying to remember. We note, okay, let's write this down actually. So logarithm function, I don't know how I'm going to write this with x is equal to log b log, I don't know how I'm going to write this. Maybe I have to go like this. No, that won't work. Log b times n. Okay. Let's get caught up on some things here. Sorry, guys. Adig, thanks so much for joining. I appreciate you leaving a comment. What book is this? This is Data Structures and Algorithms in Python. It's by a few authors. Feel free to either look it up online if you want to get access to it. You can find a PDF, or I also provide the PDF just in my Discord along with some conglomerate of the other resources I'm currently using to learn Python, such as the Python Crash Course, which I've already read. We will dive later into Fluent Python on the channel, and then eventually into Python machine learning as well. So lots of things to look forward to in the future and lots of learning to come every day, just slowly, little by little, taking it all in here. So Aaron Asher clicks on this video, guys, teaching himself Python. Dude is reading about logarithms. Yeah, I guess this isn't too beginner for... I mean, it has aspects of Python in it, right? Where we're just kind of learning about some fundamentals right now, I guess, before we actually implement into Python. So we are just doing a little bit we just started chapter 3, so we do need to do some learning before we can apply. That is crucial for learning. Desmos in the couple again. Okay, let's bring up Desmos. Okay, so we know the constant function, right? The constant function, no matter the input, no matter the sample size, we will always return the same output. So it's independent of our sample size. So log of n, let's add the n slider. What is it? Log n. We need x is equal to log n. That'd be positive. Oh, okay. So it's just a straight line? No, it slowly curves. In which direction, though? Did I type this incorrectly? Okay. Okay, do we need to do log event? No, it does the same thing. I dig subscript underscore subscript underscore. Oh, got you. Aaron Asher. I've already kind of written projects and gave myself the beginners and everything, so I'm kind of diving into more of the intermediate realm of Python in my current learning journey. So if that's something you're interested in, feel free to follow along. And I have a lot of other, if you're more beginner, and I have a lot of other very beginner friendly content on my channel, a lot of previous other streams when I was reading the Python crash course and doing CS50P. Feel free to give those a go. If you go on Desmos and input log n and say y is the time it takes to process x input, f of big N is equal to log underscore b of n if base 2 in algorithms means divided by half each step. Okay, sorry, I'm getting behind on chats here. I'm trying to read them, but also think about this. So, if you go on Desmos input login, you can say y is the time it takes to process x input. F of n is equal to log b of n if base 2 in algorithms means divide by half each step, okay? You missed a bunch of lies, so you don't context. I've been learning Python for over 6 months, my guy. Thanks, Jace. I appreciate the kind words. Thanks for stopping in. All right, we're gonna have to. Sorry, guys. There's a lot of chats here. Okay, set n to 20 and base to 2. So how do you set a base in Desmos? Oh, super. Okay, so, okay, gotcha. Okay, let's look here. Um, well, do you want y? Oh, shoot, you need y is equal to? Is that why it's supposed to be? Well, it says x is equal to in the problem. That's why I had it as x equal to. But now nothing's showing up here for my. So if we have base of 2 and n is equal to 1, what happens here? Okay, just it's like a straight line, really small. But if I go 2, it's like off the graph. I can't even see anything. Y equals, okay. Y equals. Is this just giving me values now? Oh, let's zoom out. Oh, we're way zoomed in, that's why. Okay. Okay, so then if we change sample size, okay, well then we just increase. So if sample size is 1, our base is 2, our output is 0. Interesting. Now if we increase sample size to 2, our output becomes 1. So our base just divides our answer by whatever the base is. Is that essentially, is that true? Is that all it is just a step in a sense, condition? Thank you, Anthony, for the recommendation, by the way. I really appreciate your help. And all you guys. You guys are great. Toast, everybody. Jeremy, Chase. Thank you guys. Vanch, Alfonso. Really enjoy the participation today. This is great. We're all coming together to learn and reinforce this material. So it's really awesome. Um, so log y, okay, y equals log n, theory is infinite. So you want me to delete the b? Okay, so if we delete the b, yeah, that looks more like the log I remember, right? It was like a little skew, like a little curve. Then you have some sort of asymptote. Is it at, I'm guessing it's at 1. Okay, so your asymptote's at 1 for just a basic log with an n2. Now what if we make 1? Or what if we make n 0? Okay, so n's nothing. Now as we increase n, we slowly start to branch. See, logs are so interesting how they work. You can never touch 1. So okay, so that's what it is. So as you increase your sample size, you get closer and closer to 1 until the point where you equal, your sample size actually equals the value of 1, and then you're flat, and your log will equal 0 at your sample size. Ah, your log equals 0 at your sample size of, and then as you increase further past a sample size of 1, now it'll just keep going. Now, okay, interesting. You said remove the subscript b. Okay. Okay, so there's just the basic logarithmic thing, right? Y equals log n, and it just passes through 1 and has an asymptote at positive y equals 1. So it never equals 1 in this sense. Got you. Okay, so Alfonso, thanks for the kind words. Really appreciate it. Yeah, got a haircut. Thank you. If you plug in values will become constant, leave them in as variables. Yeah, Aaron, in the back half of my streams, we work on personal projects. Right now, we're writing a small business manager project where we access and take in data as inventory lists or inventory, sort all that data, and then we can generate sales reports, hopefully process tax report documents, things like that for small business owners that might just have a simple you know, sales model. Appreciate you stopping in and commenting though. Nice. Okay. Log is the same thing. That is not. Do this. Have two equations: y equals log n and y equals n. Okay. Got you. Now what? Um, so we have a linear function here, right? And then we have a log function. All right. Have two function equations, y log n. You'll notice that log n becomes faster and faster the closer you get to infinity. What do you mean faster and faster? Like, how are you measuring speed in your mind? Like, is it just it approaches one quicker and quicker, or slow? Actually, what do you mean by that? Oh, remove n as well. I'm sorry. Wait, how I can't remove n? Y equals log n. No, I gotta keep n, you said. Faster relative to the y equals n. Okay, so you're saying that the log function. Oh yeah, it approaches in like infinity faster than the y equals n. So like at why does this zoom is terrible? Stop doing that. It is really bad. Desmos, come on. Like seriously, this is ridiculous. Okay. Oh, this is so bad. So at point 1, right, at x equals 1 on the log function, you're at 1 and 1 higher up. So as you pass 1 and you get more positive, so at x equals 3, you're at y equals 0.47, 3, you're at 3. Now, you're saying it gets faster as you approach infinity. So here you have this is getting confusing, guys. We can assume y is the amount of time it takes to process. So at x equals 2, you can see the y value for log n at that point is smaller than y equals n. So at x equals 2, right, we have a couple points here. We have 2, 2, and we have 2.3, 2 and 0.03. So then we say at that point y yeah, that point is smaller than y equals n, exactly. So what does that tell us, essentially? What are you trying to convey to me, Anthony, in saying that this value at x equals 2, y equals 3.3, whereas at x equals 2 on our linear function here, y equals 2. What does that exactly tell us? That the linear function is, now if we go like x equals, like all the way over here, you have 7.775, we have 0.8. So I guess this one continually just is faster? Is you saying that the linear one's faster? In other words, at x equals 2, it took y equals n 2 seconds to process the input, while it took log n below 0.05 seconds. Oh, that is the output. Okay, so you're saying in terms of time is the relative, what we're saying is an output. Okay, so I might not be saying this all correct. I know I'm a rookie, I'm a noob, I'm a learner, I'm ignorant. I can say that. I'm not afraid to admit it to those in the chat questioning it, but you got to start somewhere. So the hardest thing about learning something is just starting, they say. Um, so at x equals 2, right, it took the y function 2 seconds to complete the, so at an input value of 2, it resulted in a y of 2, whereas the log function completed it in almost a third, like way faster, like a quarter, not even that, like eighth of the time, right? Not even that, a third, ninth of the time. I don't even know. All right, Aaron Randall, if you're gonna just complain, man, I'm gonna have to remove you from chatting. You're not really providing any sort of beneficial input to the chat. We're understanding how things are working on the back end, so that when we can implement these into my, like, I'm a chemist by trade. I have a degree in human biology and in chemistry. I work as a formulation chemist at a biotech company for the past 3+ years, and I formulate a bunch of serum matrices by hand that takes in a bunch of n inputs associated with them. These n inputs are different types of serum values that have another set of components to them, and I have to blend them. But the only people here that seem to give some decent advice are the people actually trying to help. So let's keep it cordial, please. All right, let's get caught up in chat here. The linear function is just much slower. Got you. Y represents the time/number of operations. Okay, that makes sense. That means log n has a faster runtime than yn in the worst case scenario. In a worst case scenario. So that means that log n has a faster runtime than y equals n in a worst case scenario. Okay. So at a worst case scenario, meaning like of x equals 2, at that scenario, the log n would be fast. Okay, got you. You're looking at two functions with scale with growth of input. A linear function is much slower with the growing input. Yeah. Got you. All right. Let's go ahead and continue on here. That helps explain that. So we got logarithmic here. One of the most interesting and sometimes surprising aspects, okay, we talked about this. So for some constant b is equal to 1. Now, b is just right? By definition, log b of 1 is equal to 0. The value of b is known as the base of the logarithm. The most common base for logarithm is 2. Okay, we talked about that. Okay. We note that most handheld calculators have a button marked log. But this is typically for calculating the logarithm of base 10, not base 2. Computing the logarithmic functions exactly for any integer n involves the use of calculus. but we can use an appropriate approximation that is good enough for our purposes without calculus. In particular, we can easily compute the smallest integer greater than or equal to log b of n, log base of n. In particular, we easily compute the smallest integer greater than or equal to log b of n. So it's so-called ceiling. For a positive integer n, this value is equal to the number of times we can divide n by b before we get to the number less than or equal to 1. For example, the evaluation of log 327 is 3. Oh, so this little bracket notation is you're trying to find the ceiling. So, well, does log 327 actually equal 3? Let me see that. About, right? So the evaluation of log 3 base 327 is 3 because 27 divided by 3 divided by 3 divided by 3 is equal to 1. Likewise, log 64 base 64 is 3 because 64 divided by 4. So you just divide the base by the input value until you get to 1 to find its ceiling, its so-called ceiling. Interesting. This is really interesting. So log 12 is 4 because 12 divided by 2 is 6, divided by 2 is 3, divided by 2 is 1.5, divided by 2 is 0.75, which is less than or equal to 1. Oh, it's 4, I'm sorry. Because you are finding a number that is less than or equal to 1. So if your base doesn't perfectly divide your sample size all the way to 1, well, if you go slightly over it, then that is still the value you want. You want to go over or equal, or like not less than, but over in a terms of like downward angle. Okay. B equals base. Yep. I just think. I'm not a candidate. I'm not looking to become a software engineer. I think you're misconstruing the whole point of this, and you probably might benefit from learning something before you, or taking in some information and gathering a lot of data before you actually make a comment on something. I currently am a professional in biotech. I have a degree in physical science. I'm a physical scientist, literally, and I'm gaining additional knowledge. It's not against the law to learn new rules, right? I'm not sure what country you're from, but where I live, I'm allowed to, seek out excess education on my own front, and whatever I want to do, I can do it in certain circumstances in these lines, and I just wanted to gain additional skills and see how I could use those skills in my current occupation. There's no I think you're looking at this from maybe a competitive standpoint, unfortunately, with your current job search and your job situation. Which is yeah. I typed in 25. Oh shoot, sorry. 27, 3. Thank you for that catch, Anthony. All right. A logarithm has the exact opposite behavior of exponential. Okay. So yeah, it has the exact opposite. So it exponentially rises on the y-axis, right? Curve. Where's logarithmic? So, yeah, it's interesting. Trying to picture. It's hard. It's kind of fun to try to picture, and it helps a little bit. To solve the question log base 3 of samples n 27, the question you're asking yourself is 3 to what power gives me 27? Okay, so I'm trying to solve for the exponent then. 3 to the power of x equals 27. Solve for x, basically. All right, we had to unfortunately put Mr. Aaron on a timeout. His comments don't provide actually any value to the stream. They don't help educate me or anybody else in the stream on any concepts we're currently learning on. So they're honestly just FUD. So I think we're at 200 subs, guys, and we experienced our first comment troll. Oh boy, we become, guys? What do we become? Got you. Okay, so um, let's just finish the logarithm function here, and then I think I'm gonna call it for today. This was a lot of learning that we did today, and then we'll just do a quick recap, and then we'll call it for today, so we can kind of we need to solidify the previous stuff we learned today as well. So let's just kind of let's go through this one last quick time. So like log n is considered log 2 of n in our notation. Okay, we note that the most handheld calculators, log base 2, base 10, computing logarithmic function. Okay, we talked about this, right? The following proposition describes several important identities that involve logarithms for any base greater than 1. Proposition 3.1, logarithm rules. Given real numbers a greater than 0, b greater than 1, c greater than 0, and d greater than 1, we have, oh boy, log of b, base b times ac. Okay, so these are just basic rules for like refactoring the log. Okay, so this is like what we did in calculus. I remember this. You had like all these different rules that you could use to substitute different mechanisms and solve accordingly and to remove the expo yeah, stuff like that. Um, by convention, the unparentheses notation of log of n to the power of c denotes the value of log n to the power of c. We use a notational shorthand of log c n to denote that the quantity log n outside that whole thing is powered. Okay, in which the result of the logarithm is raised to the power. So if we see the log is raised to the power, we're not raising the n to the power, we are raising the result of log n to the power. Got you. This above identity can be derived from converse rules for exponentiation that will present on page 121. We illustrate these identities with a few examples. We demonstrate below some interesting applications for the logarithm rules in Prop 3.1, using the usual convention that the base of logarithm is 2 if that is omitted. Okay, so we have log base 2 2n is equal to, right, log base of a plus log base of c, right? So we have log base of 2 to the 2, log base of 2 with n is equal to 1 plus log n. So we just reduce this down to 1 plus log n. Okay, so you solve log base 2 is 2. 2 to the power of what equals 2? 1, right? Got you. Then we have log n divided by 2, which in theory also equals to log n minus 2, log 2. So we would log, like this results in 1, so it would just reduce down to this. Log n to the power of 3 is 3 times the log of n, log base 2 of n. Interesting, okay. And then log 2 to the power of n goes out front, log 2, you can multiply the 2 and the n to the 1 and the n to get the resulting log 2 and n together, resulting in n by itself. Got you. So this is similar to this one above, rule 3, but they just inverse the exponent for the variable. Log base 4 in this case equals n, results in log base a is equal to, no, log b of a is equal to log d of a divided by log d of b. Oh, so if you have a log of 4, you can reduce it down to log of 2 of n divided by log of 2 of 4, log base 2 of 4, which equals log of n divided by 2. Okay. And then 2 to the power of log n is equal to, you can swap a out front. There's so many swapping of variables. You swap a out front, so you take 2 times log n. You take a and put it out front. N goes out front. Log stays exponent. What does the 2 come from? The 2 is the base, the original base. No, is the number out front here. Goes up there. Which is n to the power of 1, which is n. Interesting. As a practical matter, we note that that rule 4 gives us a way to compute the base 2 logarithm on a calculator that has a base 10 logarithm button. Log equal log 4, log base 2 of n is equal to log n divided by log 2. Okay, so you can compute on a calculator with this kind of shorthand by just doing log base 2 of n divided by log base 2 of 2. Wait, but up here, oh, this is log base 10 divided by log base 10. Interesting. Okay. The author goes kind of deep into logs, which makes sense, but I think the general idea, even introducing logs in this section, that these are algorithms that can run in log n, which is what we saw. Okay. So yeah, guys, if this is kind of seeming a little bit daunting, right? Like what Anthony was saying is, I think the author is just trying to introduce the fact that these functions and algorithms can run on log n time, or something along those lines. Desmos are going to be better and more efficient than y equals n. I don't think identity. Okay, so we just kind of skip over the log identities part here. Anyways, that's kind of the end of that section, though. So I think it's just a refresh to all the students on pre-calc. Yeah, most likely better to know than not know. You don't need to know all. Okay, well, that's good to know then. So let's just quickly go over what we learned so far. So we were introduced to data structures in this lesson, which is just a systematic way of organizing and accessing data. We were also defining algorithm, which is just a step-by-step procedure for performing some sort of finite amount of task in a certain number of time. Runtime is just the natural measure of goodness that a computer solution should run as fast as possible, right? Space usage, just like memory usage, I think. I don't have a formal definition in here yet, but the epoch is a benchmark time for an algorithm, something along those lines. This one was a little bit confusing, but I think we kind of understood that. Um, we don't have wall. We don't need something for wall clock. Whatever. I'll probably remove that. Primitive operations. So these are just the most basic actions a computer can perform during a program's execution. Now we have when we want to record the time, right, of these algorithms, we can use the time module and the time function and the clock function, but these aren't perfect because the time function takes a timestamp, at the epoch, right, or the epoch, but or something along those lines. But it also is impacted by other processes going on in the computer in the background. And the clock function tracks the number of CPU cycles, but this depends on hardware. So we have a time it module, which essentially does something else, which I think it does this. It counts the number of primitive operations in the form of a variable t and measures the runtime of the algorithm. So this can be characterized by f of n, where we have some function which is dependent on n sample size. They characterize the number of primitive operations that are performed on a function of the sample input size n. So we return a value of t, which is dependent on n. Is the count. It's kind of confusing. I'm sure as we continue to go through this over the next couple of days and the rest of this week, it'll help solidify. But this is just day 1 of chapter 3, guys. We knew this was going to be daunting. So the worst case scenario. So we always, abide by our algorithm's worst case scenario because that just helps us to optimize better. It considers like all the worst factors happening at once. So if all of those were to happen, things can still be successful and might be not slow in a sense if you plan for them. So then we started to get introduced to the 7 functions used in this book. So we were introduced to the first one, which is the constant function. This took us a little bit to understand, but with some help from the chat, we were able to deduce that this function has no relation independent on the sample size n, where no matter what value of c is provided, the function will return that value provided of c. So if c is equal to 5, then f of n is equal to 5. Output will always be 5 in this case. Then we were introduced to the log function. So we had to get some refresher on our pre-calculus and calculus stuff here from 5, no, not even that. I was a freshman 3 years out of college, so almost 7 years ago when I took calculus, 6-7 years ago. Jeez, time flies. But this just basically showed us that log functions are faster than the linear functions at performing these sample size, these input evaluations and things like that. Hopefully all those were, somewhat correct. If I missaid anything, please feel free to correct me so I can definitely understand better what I'm talking about here. But so I know we're kind of slacking. We need to be more disciplined, guys, on switching over to the small business manager project. I get caught up in in learning with you guys and continuing through this book, but we need to prioritize practicing code as well as learning. Um, so we have our small business or app, and yesterday we were able to fix a bug in our child class here for sold items where wasn't supering in the right order from the parent class, and so because of that, I was getting incorrect saving and writing of items. So for those that weren't here, we wrote in the load file and save file functions the other day, and then we so now if we go ahead and run the program, actually I have a couple of just dummy I have a couple of dummy right here creations of items for an item, a for sale item, and a sold item. So if I go ahead and run this and we get into here, right, I just had a print statement to kind of extract one of these data points that was kind of giving me trouble when I was debugging. And then if we go ahead and exit and then exit out here, we go to our files, all of the attributes were appropriately written into their appropriate spots on the CSV file. Before we were getting some mismatch, and some of them were actually writing due to that ordering issue going on in our classes. But that works appropriately. So now we need to actually start coming up with a flow. We'll work on this tomorrow more. I promise. We need to be better on switching over, being disciplined on switching over to our project. But tomorrow we are going to start working on getting the run inventory. So in our menu, we're going to have a run inventory tab, and we're going to start working out that process flow for how the users are going to be able to interact with inventory, manage it, and then we'll have a transactions menu where we can actually convert items into sales, which will obviously, and then convert them into their appropriate categories, and then we'll have a tab for like report generation. Like we can generate the cost of goods sold from this month to this month, or for all of 2024. We can generate the net revenues just for this month, just for all of the year for these years. We can have all sorts of different filtering mechanisms. It sounds like a lot of work, yes, but just little by little, day by day, function by function, we should be able to slowly implement these features. And we kind of have been building up to this point. Don't think that Rome was built in a day here, guys. Before this, I built a very basic and very simple. I didn't even save the file, the information, the data. It just deleted it after the program ended. For my CS50P final project, I have a video on my channel that displays that for that final project, but for that assignment. But it just is a inventory storage system. So we made that, and then in our next project, we made a task tracker application, which utilized aspects from that learning we did in the inventory storage system, and then we applied even more aspects. We implemented saving and writing files, writing and reading files. We implemented filtering of filter mechanisms. So now we're going to put that all together even more and create another project under a different type of mechanism for a completely different avenue, but still kind of all along those basic principles, just put to a different use into this. And so it's been the course. I've been doing these projects since started. I submitted that project, and it was for CS50P, the initial one, back in August, the end of August, beginning of September, and I was working on it from about July all the way through August, because it took me a long time to get through, because I was very new and still learning. But make sure, thanks you so much, you guys, for 200 subscribers on the channel. It's absolutely mind-blowing. I never thought, well, I was hoping people would enjoy coming in here and watching and learning along, and also learning themselves as I'm putting myself to the test here. But it's just truly crazy that people are actually really enjoying it. So which is just awesome to hear. So I'll see you guys tomorrow, same time, about 7 p.m. PST to about 9:30. And then on the weekends, I'll stream, anywhere from 2 p.m. all the way till 8 p.m. or I'll stream for a long time on the weekends. This is I'm really serious about learning, adding new skills to my current skill set of biotech and chemistry. And yeah, so I'll see you guys tomorrow. Thanks so much for 200 again. You guys are great. Tons of input today, learning DSA, breaking into these. Like I said, it was a ton of new material. Don't, if you're learning this with me, don't feel, anguish that there's just too much, right? It's a day by day thing. It's a page by page. We can always go back and relearn. We can always, it's not the end of the world. Time is our friend here. It's not against us. So anyways, thanks so much for coming in, you guys. See you tomorrow. I know I ramble on a lot, but see you guys.